So now we're going to look at some representative experimental designs, just the kinds of designs people actually use. One's called completely randomized design. In a completely randomized design, it says the treatments are randomly assigned. So you take all the subjects and you assign treatments randomly. So it's called completely randomly designed or completely randomized. The question we're trying to answer, can a household be influenced to reduce energy consumption? The explanatory variables are the various kinds of interventions we're going to take. Energy meter installed inside the house. So you just see your energy bleeding out of the house. Website can be accessed, so they give you access to a website to check your consumption. So anytime you wanted to log on, you can see how much energy you're using or how much you've used up to that time. And then the control treatment says the usual energy tips are included with the bill. So everyone gets that. Even these people get the energy tips included. So it's just a default situation. We'll take the 60 households that we have lined up to take part in the study. We randomly assign them into groups, 20 in each. And the first 20 get treatment 1, energy meter. The second group of 20 gets the website, and the last group gets the control, just the usual tips included with the bill. And at the end of the day, we're going to compare energy use this year versus last year to see if the energy use went down this year compared to last year. Now you might wonder, what's the purpose of this control group really? Because really we've got these interventions. They ought to do something. Let's just see which one is better. True enough, but we want to be able, might want to be able to measure exactly how big an impact those interventions had, not just to compare the two of them to see which one's better. How much influence did it have? So we want to compare it with no interventions at all. In addition, one of the drivers in energy use is the weather. And so when we compare this year versus last year with the control group, we're comparing the weather. What influence does the weather have on energy consumption this year versus last year? And once we've taken that into account by looking at what happened to this control group, again we can see what extra benefit we got using these interventions, if anything. So without the control group, we won't really know whether the interventions actually worked, because we might actually see energy consumption go up because the weather was either hotter or colder when we would need to be using energy to control that, and then it would look like neither intervention worked without looking at the control. So the control says, here's how much it would have changed without intervention. Then we can see the difference between that change and what happens in the households. So that's a completely randomized design. It's called completely randomized because the households were randomly assigned the treatments without any other information being collected from the household, just randomly. The second kind of design we're going to talk about is called a randomized block design. Blocking is dividing the subjects into groups that have similar characteristics. So blocking divides the subjects according to some explanatory variable. So they come with that variable attached. You can't change it. People come either being men or women. And if you think that the treatment might be impacted by whether you're male or female, which happens a lot with drugs, that men will be susceptible to the impact of one drug and women to another for a particular condition, then if you're trying to test drugs against each other, you want to test them in a gender-specific way. So you do a test on the men, you do a test on the women separately of the two drugs. Otherwise, if drug 1 works better on men and drug 2 works better on women, and you mix the subjects up, it's going to look like the drugs are actually have the same efficacy, when in fact one works a lot well for men and not the other one doesn't work so well for men, and vice versa. So that's what happens if you mix those two together. So it makes sense to divide them up in blocks. There are other blocks you might use based on pre-existing conditions, things like that you might want to block the subjects on, because The effectiveness of the drug might depend on other drugs they're on, what their age is, different things. So blocking makes a lot of sense. One story I like telling is that a particular treatment that's found to be gender specific is carbo loading used for marathons and other endurance sports. Carbo loading was tested on men and found to be effective. Turns out when they tried testing on women, it wasn't very effective at all. And we just assumed, since it worked for men, it worked for women. And I think that the medical establishments, since it's mostly men, had that feeling that men or women are pretty much the same. And most of the tests they tested were just on men. Usually the physicians would volunteer for a study or something like that. They were mostly men. And so heart disease, carbo loading, other kinds of things are gender specific in response. And so now we're careful when we have medications to do at least test them on men and women separately and try not to mix those responses together. So here's a randomized block design. We're comparing two fever medications. We're assuming there might be a difference in response based on gender. And so since that could happen, we divide the subjects into two groups, men and women. We randomly assign the subject then to groups. So we split the 600 men randomly into two groups, the 600 women randomly into two groups. First group gets drug X, second group gets drug Y, but it's been a random assignment. And then we'll compare the fever reduction. We're talking about fever medication. We'll see how much fever gets reduced in those that took drug X and those that took drug Y, see which one's better for the men, see which one's better for the women. And I suppose we might say, then we'll just compare the compares. Because if those reductions seem to not really depend on gender, then we can make recommendations that this drug works both for men and women. Otherwise, we can say, well, this drug works better for both men and women. Otherwise, we could say X might work better for men and Y might work better for women by comparing these once we've decided which one seems to be better for each gender. So we talked about the purpose of the blocks. That's to ward off any problems might happen that because of a gender-specific response. What about a control group? So what would the control group look like in this case? You might want a control group where an extra group was here and the drug was the usual drug. Maybe you use aspirin to try to reduce fever and do that for both of these. Maybe you want to do that. On the other hand, the situation might be that previous studies have shown that drug X and drug Y are pretty effective at reducing fever, and just from experimental evidence of some other experiments that might have been carried out, but they just don't know which one's better. So this is telling which one's better, not just necessarily whether they work better than aspirin. If they already know they're both significantly better than aspirin and you want to know which one works better, you do this. If you don't know much about them at all, you just want to compare to aspirin, then you'd have a control group, a drug group, and a drug group. You'd still have you still have to do the gender thing. Aspirin's not very gender specific, but these drugs might be. So in the comparison, I guess we'd have to run them all across like this. And if there's 600, we put 200 in each group. And then compare and compare once again. And that ends one of the two most popular experimental designs you might run into, the completely randomized design and the randomized block design. And now we'll move on to the next experimental design in a few minutes. One of the purposes of this section is to show you how to make a diagram that represents the experiment so you could show somebody exactly how it unfolds and what you're going to do. It's pretty hard to do that with words. It's a lot easier to do it with this kind of a picture. And that's what those kinds of pictures look like. And it's useful to be able to display them if you want to explain to someone who's looking at experimental evidence exactly how it got collected and how it was analyzed. And we'll move on to the next kind of experiment in just a minute.